So hello everyone again. Today we are going to talk about an interesting topic, that is how to clean and organize the knowledge graph with a focus on the disambiguation process. And I wanted to quickly introduce ourselves. I'm Federica, and with me my colleague Alessia. We are data scientists at Graphaware. Graphaware is the world leader in solutions and training for Neo4j-based graph data, and the creator of UM, a graph-powered insights engine. And just running through the agenda, we are going to talk about how to build a knowledge graph starting from unstructured data with a real use case we dealt with. And we will focus our attention on the disambiguation of keywords, on the named entity disambiguation process performed using two different approaches. The first one is based on lexical similarity, while the other one on semantic similarity. And lastly, we will visualize and evaluate the final results going through a UM demo. And I just wanted to mention that we will answer all your questions in the chat room, because I think that we won't have enough time. So let's start this journey with a real use case coming from Rockefeller Archive Center, that is a major repository and research center for the study of philanthropy throughout the world. And its archive contains historical documents and materials on the histories of science, medicine, public health, and a lot of other topics. But what do these documents contain? These documents are different, but they generally describe the conversations that the foundation had with people or organization, and they provide information about research on particular topics, disciplines, and research fields, and the related awarded grant for this research. And something that it's worth noting here is that these are historical documents, and this is something that we need to take into account for the further analysis. Indeed, if we observe the date of this document, we can notice that it comes from the first half of the 20th century, and it was the same for all the documents that we studied, starting from 1930 to 1940 about. And moreover, these are typewritten documents that have different contents and structures. And about the analysis in which the Rockefeller Archive Center is interested in, this is related to the grants awarded for topics and research fields. Particularly, they asked to find the disciplines that have received the most grants, such as molecular biology, that was one of the emerging fields at that time, and being able to describe the evolution of fields over time with the decline and the rise of different fields. And the topics are the information on which we will focus our attention from now on, that are disciplines and research fields, essentially. So let's start from the information extraction pipeline that we applied for obtaining this information from the documents. The first step that we applied involves an optical character recognition tool, and it enables the conversion of typed text into machine-readable text format. And we needed to apply this step because the documents that the Rockefeller Archive Center provided us were scanned typewritten documents that were in PDF files, in PDF format. So we needed to perform this task for obtaining the machine-readable text, starting from this. After this, we applied the named entity recognition. We used a named entity recognition tool that identifies named entity mentions in the text, and it classifies them into predefined categories such as person, organization, location, and so on. The third step, that is the most important for our analysis, for the purpose of this topic, is the disambiguation process, the named entity disambiguation or linking. That is the process of assigning a unique identity to entities mentioned in the text that are found by the previous step, the recognition step. But I just said that the third step is the most important for this purpose. But why name entity disambiguation is important for our analysis? Because disambiguation is strictly related to the grant analysis, because the grant analysis depends on the ability to organize and group research fields. And if we are able to find all the subfields or or all the sub-disciplines of a field, if we are able to understand that hormones is an object of study of the endocrinology field, in this way we are able to perform a more accurate and a complete analysis. So name entity disambiguation task is generally performed against a knowledge base that could be Wikidata as represented in the picture, or a medical ontology, or any other dataset that could be used as a ground truth. But in our case, it was difficult to find a knowledge base for the disambiguation of topics, and this mainly for the following reasons. First of all, we are dealing with words and expressions from different areas, such as biology, social sciences, medicine, and so on. So we needed to find a knowledge base that involves all these different disciplines, that contains all these different fields. And again, a lot of these expressions are historical. So this is another requirement that we needed to take into account. And the keywords have, again, different granularity. Some of them are very specific, while others are more generic, such as in the reported example. And for these reasons, and since we were having difficulties in finding a knowledge base for the disambiguation of topics, we tried two different approaches. The first one is a lexical similarity, while the second is based on semantic similarity. We will describe both of them, and we will see what are the drawbacks of the first one and why the semantic approach is the most suitable for our purposes. Okay, let's start from the semantic approach, from the lexical approach, the lexical similarity. And we can say that the lexical similarity is a metric that measures the distance between documents, expressions, sentences, or even words based on the number of common characters. And the first way in which we performed the disambiguation using the lexical similarity is based on substrings. Particularly with the reported query, we are creating a similarity relationship between the two topics in case the name of one of them is contained in the name of the other, and particularly the name of one of them starts with or ends with the name of the other. And as we can observe in the table, we obtained some good results, but something that we noticed in this case is that we were not able to create a similarity relationship in case a topic, the name of a topic, contains some typing mistakes. And this was that often happens in the document, because these are typewritten documents, so it is something that could happen. And for this reason, we decided to perform the lexical similarity using also another similarity that is based on Sorensen-Dice index. And this time we used the Sorensen-Dice similarity that is implemented in the APOC library. In this case, we are creating a similarity relationship between two topics in case their names have a similarity that is higher than a threshold, 0.85 in our case. And we found this threshold empirically by observing the results of the similarity score. As we can observe, we solved the first problem, the problem with typing mistakes, because we were able to create a similarity relationship between human behavior and the same word, the same expression, but with some typing errors. A problem that arises in this case is related to this example, biological laboratory and physiological laboratory, and it is related to the fact that the strings are not completely able to represent a concept. And in this case, we have actually a high similarity, while these two topics could be different from each other. And also for another reason, we decided to change this approach, and the reason is explained here. What happens with the keywords like endocrinology and hormones? Because the two, we know that endocrinology is a science that deals with hormones, but these two strings are different, so we cannot define a similarity relationship using the lexical approach. And this is the reason why we decided to use also another approach that is based on semantic similarity. And semantic similarity is a metric that measures the distance between performed expressions and sentences based on the similarity of their meanings or semantic content. And we performed this approach using two steps. The first one involves a sentence embedding algorithm that understands the meaning of a sentence and it represents this sentence using a vector with its meaning. And the second step involves a clustering algorithm that clusters and groups vectors that are close in the vector space and that represent similar sentences. And let's ask Alessia to explain better this semantic similarity approach.
Hi, everyone. Thank you, Federica. So, so we are talking about how we want to exploit a semantic similarity approach to achieve the disambiguation without the use of a knowledge base. So let's start with the first step, the sentence embedding. So what is the sentence embedding? It is a technique that maps sentences or words into vectors so that sentences with similar meanings are represented by vectors that are close in the vector space. We use sentence transformer Python framework to achieve the to compute the embeddings that is based on transformers and offer a large collection of pre-trained model suitable for different use cases. We decide to use this model and simply apply the encode method to the model with sentences as input. In this way, we obtain a vector of about 700 of dimensions for each topics. So now we have the embeddings that capture the similar meaning of the topics, and we want to group this embedding, the topics, in such a way that topics in the same group are more similar in some sense to each other than to those in other groups. And this is a well-known problem, and it is known as clustering. So a cluster can be defined in a different ways. For example, small distances between cluster members, dense areas of the space, and all these definitions have one only common denominator, that it is that a cluster is a group of similar data objects, and for this reason, the clustering is not one specific algorithm, but is a task of grouping objects. So we need to choose the algorithm that we want to use, and this choice depends on the problem we are facing, the data set, and the intended use of the result. We can say that the clustering is in the eye of the beholder. So for this reason, we explored the results for different cluster models, and we started our investigation with k-means, that is a centroid-based clustering method, where each cluster is represented by a central vector, and k denotes the number of clusters that has to be fixed. In this picture, we can see, for example, the clusters relative to the keyword vitamins for different value of k, 80, 140, 200. And if we look at the intersection of this cluster, we can see that they have only a few topics in common. So we can say that when we change k, the results are not stable. So it is very hard to choose the right optimal value of k. For this reason, we try to exploit the DSCAN algorithm, that is a density-based clustering method, where the clusters are defined as high density areas, where the density is defined as the number and the closeness of the points. The closeness can be established through a parameter called epsilon, and in this picture, so by increasing the value of the epsilon, we can obtain larger cluster. So look at this picture. We can see that for epsilon equals 0.3, we have these three clusters related to the keywords tuberculosis, linguistic, vitamins, and so on, that are very small. And when we try to increase the value of the epsilon to obtain a larger cluster, all these three clusters are merged together, and the retrieved cluster contains more than 1,000 of keywords, and they are not, and this cluster is not related to a specific topic anymore. So for our purpose, this is not the best value, because we want to find, to retrieve consistent clusters that we mean a bigger cluster, but related to a specific topic. For this reason, we try to exploit a very different method, clustering method, the hierarchical clustering, that it is the method that best fits our expectation, our needs. And what is a clustering hierarchical clustering? Is a method that seeks to build a hierarchy of clusters, as its name says. And this hierarchy could be represented by a dendrogram that is a tree, where in the root there is a single cluster that collects all the samples, and in the leaves we are the clusters with only one samples. But hierarchical clustering is a family of algorithms, but it can be divided into two categories, divisive and agglomerative clustering, and they differ in a way they build the hierarchy. As we can see in the animation on the right, the agglomerative clustering build the hierarchy starting from the leaves and iteratively merge the cluster until only one cluster is retrieved. But how we choose how to merge the clusters, which clusters merge, we need two elements: the distance that defines the distance between 2 points, 2 samples, and could be Euclidean distance, cosine distance, and so on, and the linkage criterion that defines the distance between two clusters, and the pair of clusters that minimize this criterion will be merged. Example of linkage criterion are single, complete, and average linkage that defines the distance between two clusters as the minimum, the maximum, or the average distance between all the samples belong to both the clusters. So we say that agglomerative clustering builds a hierarchy, but to obtain flat clustering, we will cut the dendrogram to a certain distance threshold above which clusters not merge. For example, if we look at the cut level A, we can see that we retrieve 3 different clusters. And if we cut the dendrogram at the level C, we retrieve only one cluster that contains all the samples. So in this way, by changing the distance threshold, we can choose the granularity of the clustering. So by increasing its value, we can go from fine-grained to coarse-grained clusters. Now, we have all the elements to try to compute agglomerative clustering. So we exploit the implementation of agglomerative clustering available in scikit-learn Python library. And it is very easy to achieve agglomerative clustering. We need only to set a few parameters. For example, in this example, we set the affinity and the linkage as Euclidean and average, and in the distance threshold as 1.8, and the number of clusters must be known because we can set only one parameter at times between these two. And then on the same row, we apply the fit method that take as input the data set that for this example is composed of 6 points, 6 two-dimensional points. And instead, in our use case, in the Rockefeller Archive Center use case, the dataset is composed of the embeddings that we compute for the extracted topic. Instead, the affinity is set as cosine because it is the best metric that captures the closeness of the embedding. On the right, we have the plot of these 6 points where the marker indicates the cluster. So a problem arises when we try to increase the size of the input. So to mitigate this problem, we can take advantage of the parameter connectivity, which is a sparse matrix that for each sample defines its neighborhood. So in this way, we can highlight the structure of our data. And for example, in this code, the connectivity is defined as key neighbors graph, that for each sample, we take the key nearest neighbor. But this approach has some limitation. For example, if we look at the picture on the right, we can see that in the neighborhood of the point A, there is the point C. So this model can consider as close points that are far away. So to solve this problem, we can decide to to use radius neighbors graph that defines the neighborhood of a point as the points that lie within a given radius. And as we can see, the point C doesn't belong to the neighborhood of the point A. But if we look at the point D, we can see that in this neighborhood fall a lot of points, and in our dataset we have a lot of points like D, and so in this way the size of the input of the agglomerative clustering doesn't decrease. So to solve also this problem, we decide to use both the approaches together. And so first of all, we compute key neighbors graph, and then we take only the points that fall in a given radius. And so, as we can see in the picture, all the problems arise are no longer present. So now we know how to compute agglomerative clustering, but how do we choose the distance threshold that best fit our needs? First of all, we can compute the agglomerative clustering for different distance thresholds, and then we can try to explore the hierarchy. But tables, prot, or similar tools are not the easiest way, we can say, to explore it. But before we say that the hierarchy could be represented by a tree, so graphs come to help, and so we can start our demo on the U. So to explore in an easy way our result, we created this simple schema where the topic node corresponds to the disciplines and the research fields that we extracted from the document that are linked through the belong to cluster relationship to the cluster node. And so each topic is linked with its own cluster. And then we have this hierarchical is-in self-relationship for the cluster node that allows the creation of the hierarchy. In the end, we have the distance node that correspond to the distance threshold that we choose for to compute the agglomerative clustering. So to explore the data, we can use Hume's action, and we start with this one that build the help us to serve the hierarchy. So we can retrieve a subtree of tree level. We can see how we can choose a topic, throw its name, and then we take its own cluster for the distance threshold that we choose as parameter. Then we match the subtree rooted in this cluster node, and for the lift cluster node, we take all the topics that belong to the cluster. So let's try to run this query. For example, for the keyword Earth, for the distance threshold 0.8. And we obtain this visualization. As we can see, this is the root node of this tree. That is a cluster node for the distance threshold 0.8. And as you can see, the keyword Earth belongs to this cluster. So let's try to explore this tree. We can start with these clusters that is related to very related to the keyword Earth. And then if we go up to the level 0.7, we can see that this subcluster, it is merged with this one that talks about Earth disease, Earth attacks, so it's related to Earth disease. Then if we try to explore with which cluster at level 0.8, this one is merged, we can try this that talks about circulatory system, vessels, and so on, and this one that talks about blood. So this exploration highlights how increasing the distance threshold we can obtain bigger clusters, but still related, we can say, a specific topic. And another query that we can try to explore our result is the following. we can get these two topics node, endocrinology and hormones, and we can apply this query that returns the smallest clusters containing the two selected problems. So as you can see, with the semantic approach, we can consider these two keywords related very close. And if we try to explore how the cluster of the keyword endocrinology is for the distance threshold 0.4, we can see that the result that we get is very close to the result returned for the lexical approach. But the semantic approach allows us to increase the distance threshold of the agglomerative clustering, and so we can retrieve clusters that put together keywords with higher level semantic similarity. So this is the way how we explore our result. And so Federica will show us how we use this result for our use case, for Rockefeller use case. Federica, the stage is yours.
Thank you, Alessia. So, okay, thank you. So let's come back to our initial question. We wanted to analyze the evolution of grants awarded for topics and the research fields over time. And let's do this by exploring the results that we obtained using the semantic approach, going through a Hume demo. Sorry. Okay, so here we can see all the information that we need for this analysis. We have information about grants awarded for topics, along with the clusters that have been created using the agglomerative clustering and the semantic approach. And something that it's worth noting here is that we selected as a distance threshold 0.7 because this was the threshold that best fits our requirements, our needs. So for this reason, all the following queries will be performed using this threshold. And let's suppose that we wanted to know, we wanted to have information about all grants associated to a cluster, to a topic. We can use this action that takes as input a topic and will return all the grants awarded for topics that are in the same cluster, essentially. That means that are similar to the selected one. Okay, if I run this query using, for instance, hormones, because we know that we expect to have hormones and endocrinology in the same cluster in the final result. So we can observe that we have all the grants awarded for endocrinology that are on the right, on the left, and all the grants awarded for hormones on the other side. And we can say that the total set of grants that we can see on the canvas have been awarded for topics related to endocrinology and hormones. If we run again the same action, maybe for chemistry, so that we can investigate another cluster, we can say that we have a lot of grants awarded for chemistry, but also for organic chemistry and its of organic reactions. And something that we can notice is that for each grant, we have information about the date when the grant was awarded. We have the name of the grant and the total amount, the total money that are associated to this grant, to this selected topic. And let's start the investigation over the evolution, about the evolution of grants over time. We can do this using this query that essentially takes as input a topic, and by selecting the distance threshold 0.7, as I said before, it returns the evolution over the years of the grants awarded for the topics that are in the same cluster. So we can observe that for each year we have the total amount of grant for the selected cluster. And if I run this one, maybe selecting organic chemistry, taking organic chemistry as the starting point, we will have this as the result of the evolution of grants related to chemistry, on organic chemistry, and related topics. And something that we can observe is that a great amount of money was awarded in 1939, almost $200,000. And if we want to know more about this year, we can use also another query that takes as input again a topic and a specific year, and returns how the grants have been divided over the specific cluster and on the selected year. And let's run again this other query by selecting the year that we are interested in, 1939. We can observe that a lot of grants are associated to organic chemistry, but also something else for chemistry. This and more complex analysis could be done using a graph, as we know, and using also Hume. Okay, so we were able to discover that the semantic similarity approach performed using transformers and agglomerative clustering helped us to clean and organize the knowledge graph for Rockefeller Archive Center use case. And if you want to learn more about Rockefeller Archive Center use case and how to turn archives into knowledge graphs, you can watch the record of the talk of our lead data scientist, Vlasta. And if you want to know more about clustering applications and how to analyze temporal graphs, you can follow the talk of our lead machine learning engineer, Fabio, that will be in about an hour. So thank you so much. I think that we won't be able to answer your questions live, but we'll do it in the chat room. And yeah, otherwise you can reach us at the provided contacts, and we'll be more than happy to provide more details and answer your question. Thank you so much.
Thank you guys very much for this very interesting presentation. I think that we have time for a couple of questions, if you're up for it. We have one here from Mark. One, did you publish a paper? Two, with the clustering upon Neo4j, do you still use hierarchical algorithm which you presented before, or is it quite substituted?
So we didn't publish a paper, and on Neo4j in GDS there are community detection algorithms that we try to use, but hierarchical clustering works well. I don't know if I answer to your question.
All right. So we have a couple of questions that got answered in chat as well, but for the sake of the stream, I thought that might be interesting to answer some of them in the video as well. Okay. And we have one here that says, what favors Soren's dice against Levenstein's difference to account for spelling mistakes?
Based on our experience, they are quite similar metrics. So essentially, the problem is the same, that the language is let me say that the lexical approach could have a lot of limitation related to the real meanings and the content of a word, that sometimes it's hard to capture using only the string itself.
And with low distance threshold value, we can capture all the typo. So at the end, we chose this method.
All right. So we had a clarification here from Mark, and he asked, did you give up the hierarchical algorithm with scikit-learn? I'm guessing that's okay. Let's skip that question. And thank you guys very much. And you'll be around in the chat to answer some more questions if there is anything more. It was a very interesting talk. And thank you for speaking here at NODES.
Thank you.
Thank you.